So this is the assembly language course, and we're down to chapter 8, which is the most significant part of it really, 32-bit x86 assembly. So let's talk about this here. So we're going to do the basics of assembly and a few somewhat more advanced features, but the basics are mainly what we're going to focus on in this course. So here's some basics. If you have a 64-bit operating system, which is pretty much the only one anybody's going to have these days, you can run 32-bit code on it. Now, Windows always supports one version back automatically. Linux does not unless you add optional libraries, and here's the commands that do that on Debian. This multi-lib and such gives you the ability to compile 32-bit code and run 32-bit code. You put a -M32 when you compile, and it will make 32-bit code, which is what we want to do at this point because 32-bit assembler is a little bit easier. And once you understand that, it's pretty easy to make the jump to 64-bit assembler later. Now, one problem is the syntax. There are two syntaxes which are different. Linux typically uses AT&T and the GNU assembler. Microsoft uses Intel syntax and Microsoft's assembler, or Linux's equivalent assembler. And the main difference is the order of source and destination. So when you have, when we get to assembly code, I'll show you that. Anyway, so he can get into it. Here's a program adder, and this will just have a main function that sets x equal to 40 and x equals adder 2 of x. So it calls this function, which returns a plus 2. So if you send it 40, it'll return 42. It'll put that in x, and then it'll print the value of x in decimal and return. So you compile it with -M32, and you'll have a 32-bit code. And if you do obj dump, you can dump out the assembly code and see the adder function. Remember, adder function just takes an input parameter and adds 2 to it. So what you have here is the preamble that creates a stack frame, which we're going to go through this in some detail a little bit later. But this adjusts the stack pointer and the base pointer to set aside a new region of the stack and make it 8 big. I think it's going to push EBP. That saves the old one. Then it's going to move EBP into ESP. Now here I can talk about this Intel versus AT&T syntax. Now I think this is the AT&T, which is, and in the AT&T, it's source on the right and destination on the left. And the way I can always tell is I look for a constant value like 2. This command will put 2 in EAX, because it can't possibly put EAX in 2, because 2 is an immediate value. It's not a storage location, like a memory address or a register. So this must be the source here. So it's source destination there. I said it wrong. So this is the one, yeah, that makes sense. The one I'm less familiar with, the one, not a Microsoft one. So this is the source, that's the destination. So this is going to take the stack pointer and put it in the base pointer. And that's going to create a stack, a new stack frame, of size 0, apparently. Oh, that's right. That's right. And let me go back here. The reason it's size 0 is because parameters don't go in the local variable. Now, local variables like this int x go on the stack frame. But this subroutine has no local variables at all. It has a parameter, and it adds 2 and returns it, but it doesn't have any local variables like int or char defined here, so it doesn't need any room on the stack. So when you enter it, it just moves ESP into EBP, which starts a new stack frame of size 0 with ESP equal to EBP. So that's what's going on here. Then you're going to take the value 8 past the base pointer, which is out of the current stack frame. That's where parameters live up there, and put that in EAX. Then it's going to add 2 to EAX and pop and return, because the return value is traditionally in EAX. So putting it in EAX means when I return, the calling function will look in EAX to find the return value. So that is the function that adds 2 to the parameter in assembly code. All right, so there's registers A, B, C, and D are general purpose registers, and they are EAX because they're originally an 8-bit register and then extended once to 16 bits and extended again to 32 bits, so they're extended A extended. This would be a 32-bit register. Then you have EDI and ESI, which are, again, general purpose registers usually used as an index in a loop to do something like copy a range of memory. And then ESP and EBP are the top of the current stack frame and the bottom of the current stack frame. Is the frame pointer the same as the base pointer? Yes, that's right. They can call this the frame pointer, exactly. So EBP is the frame pointer, points to the bottom of the current stack frame, and ESP points to the top of the current stack frame, and that's the area where you put local variables. So that's the game, and EIP is the instruction pointer, which is the address of the next instruction to be executed. All right. So you can also, so most of the time you have 32-bit code, and every operation processes 32 bits of data, and you use these registers I just described. But if you're running legacy code compiled for an early version of a processor, you might want 16-bit or even 8-bit processing, so it is possible to refer to just 16 bits of the registers, or even just 8 bits of the register. And sometimes you might do that to run really old code, but the main reason people do it these days is to make hacking code that can be injected to make the code smaller and to avoid having null bytes. Anyway, all right, so here's an instruction, add 2 to EAX. The opcode is add. That is the mnemonic that tells you what function is going on. And here's the operands, 2 and EAX. A constant literal value is preceded by dollars. Registers have a percent. So this dollars means this is an immediate value of 2. 0x means hexadecimal. And a percent EAX means it's a register, EAX. So you take the immediate value 2 and put it in EAX. Now, if you have this 08x parentheses percent EBP, that means take the value in EBP, add 8, and go to that memory location. So that would not change the value of EBP. It would use the EBP as a pointer and dereference it and go to that memory location. Here's a possible immediate memory address. All right. So here's some examples. ECX is a register. This EAX with parentheses means take the value of EAX and go look up that location in memory. So if you look at the example values here, EAX contains 804, and so the memory location 804 contains CA. So this would refer to the value CA that it got by looking it up in the memory. This is an immediate constant, which is more than 32 bits long, 808. It's a memory address, but I mean, it's just a constant. This is memory without the dollars. I see. I thought it was the parentheses. Okay, so without the dollars, an immediate value refers to memory address. That's interesting. I didn't know that. I thought you always had to have the brackets or parentheses around it, but that's because I'm used to the Microsoft syntax, which is the Intel one, I think. Anyway, so that's a memory address, which would be 808 FD. This is adding 8 to the memory address EAX. So you go to EAX, which is 804. You add 8, so it becomes 80C, and then your address result is 12. All right, this is going to be adding these two together. So EAX plus ECX, so that's going to be 804 plus 4. So that's going to be 808, so that'll be the value FD. This one is going to be take EAX, add ECX, and add 4. So it's going to be 804 plus 4 plus another 4, which is going to be, again, 80C, I think. Yep. So that one was 808 for FD, and this one was 80C for 12, all right? And here you've got 0x800, which is a memory address, and then you add EDX times 4. That's what this comma stuff is, comma EDX, comma 4. So EDX is the count number of 4-bit words to move through. EDX is 1, so you'll add 4 to this, you'll get 804, which will give you a CA, all right? And here you're going to take EAX and EDX times 8. So that's going to be EAX is 804, and EDX is 1 times 8, so that'll be 80C again for 12. So that's an example of how to read these things. All right. So you can't, like I mentioned, this is how I always tell which way the source and destination are. Find a constant, and the constant must be a source. It can't be a destination. You can't write anything onto 2. You can write things into memory address 2, but the constant 2 is not something you can write into. All right, and you can't have memory on both sides of the instruction. You have to have a constant or a register on one side or the other. And when you're using these ones with the scaling factors here, You can't just use anything. It has to be 1, 2, 4, or 8. The purpose of those scaling factors is to move forward a group of bytes. For example, if you want to copy a whole region of memory, you would copy a 32-bit word and then move 4 bytes ahead and copy the next 32-bit word. So you'd jump by 4s. And these are the sizes of common variables that they've made possible there. So the common instructions are like move, add, and subtract. They're all pretty obvious. This will move source to destination. Copying it, this will add the source to the value in the destination and store the result in the destination. This will subtract S from the value in the destination and store the result in the destination. And you can have a suffix which tells it how big how much data you want to process. B will process a single byte, W will process 2 bytes, and L will process 4 bytes. Remember, you got regions of memory stored here. There's going to be a stack here, and you'll have a little bit of this portion for your process, a stack frame. There's a heap here where you can allocate temporary storage, and then code and data in the operating system or elsewhere in memory. So to manage the stack, you can push and pop. When you push, it'll push this 32-bit word onto the stack and decrement ESP by 4 to make you point to the new top of the stack, place you can put things. And therefore it's the equivalent of this. Subtract 4 from ESP and move S into the address pointed to by ESP. That will add it to the stack. Pop will do the opposite. It will take data from the stack off, put it in the destination, and then increment the stack pointer by 4 to make the stack frame smaller. It doesn't erase the data in the stack. It just indicates that it's no longer in current use and available for reuse later. So let's try this stuff live. I've got a Linux machine running on an Intel processor I've connected to here. And so the code is adder2. So let's take a look at that. All right. And so here you see it. This is the function that adds 2 to the parameter and returns it with no local variables. And here's the main function that sets a local variable to 40 and calls adder2 on that and prints it out. So if you run this program, it prints 42 because it took this 40 and added 2 to it. And we want to see how it works. And we're going to do it in the debugger. So we'll debug it. And I don't want the colors because they make it hard to see things. All right, and break star adder2. I'm going to let it run to adder2. So I run. Now, then it's ran to where it's entering. Are the registers all in stack? No, the registers are separate memory locations in the processor. Here, let me get set up here and I'll talk about it. I'm glad you're asking. Disassemble adder2. And then info, let's look at the registers. There, you remember you have main memory, which is, like 4 or 8 terabytes or gigabytes of stuff. And you have these things here, EAX, EBX, ECX. Those are special memory locations on the processor itself. There's not very many of them. So those are stored on the processor. They're very fast to access, and you use them as a temporary scratch pad because they're constantly being reused by every instruction. So you want to save anything for any length of time, you copy it to RAM. It's a good question. Right, so here you see I put a breakpoint here at the start of adder2. This arrow tells you where I am. So I've stopped here. So I have not yet entered this function. I'm about ready to enter this function. So right now, the stack frame goes from 488 to 4A8. So that's 20, which is 32 bytes in hexadecimal. And so that's the main routine. The main routine stack is about to enter this. The first 2 commands here are going to create a new stack frame. So the ESP is here at 488. That's the next available stack area to use. This is going to push EBP onto the stack for later. So I can restore it when it's time to return. And it's going to move ESP to EBP. So they'll both be the same. So if I execute the next 2 instructions, which should be here. All right. We've talked about this. All right. Yep, I explained all that. So now I'll do this stuff. So next I will do 1 machine language instruction. And next I again will move ahead. And now I can look at the situation with disassemble and info registers again. So now I've moved forward 2 instructions. I've gone through the preamble. And the preamble creates a new stack frame so you can see ESP and EBP are now 484. So the stack has size 0 in this subroutine because it has no local variables, and I've got a region of stack memory that does not overlap with the stack memory of the calling function. That's the idea. So now, all right, and I can also look at the stack with x12x ESP. And here's the stack. Here's 484, which has got nothing on it, but that's the stack frame. Right after the stack frame, you've got the return pointer, which starts with 56. And you can see the instruction pointer here points to 56. On this machine, compiled code execution all starts at 56. That's where it puts the compiled code. So this is a real address pointing back to the instruction after the call function in the main function, where it's going to go back to. All right. And the epilogue is what happens at the end. When I'm done with this function and it goes back, it will pop EBP. It'll restore the EBP off the stack and then return, and that will let us go back to there. So let me try that. Next, 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 and return. Let's do that. Next, I, next, I, next, I. And when I notice these are sequential, 93, 96, 97, that's following these steps. The return will jump back to the return pointer, which is this address ending in 1B8. So when I take one more step, now I'm at 1B8. And now if I do info registers, I'm back in the calling function, and again I have a relatively large stack. So I'm not, that's what happened. I've restored the stack frame, so the stack environment is back to the environment of the main function. The context of the main function is another way to say it. So let's try a Kahoot. Garbage. All right. This should be 6A. Oh, 8A, right. Okay. Ah, good. They're not quite, didn't sort in order as well as it should have, but anyway, that's life. All right. All right, maybe we only got 2 players today. Apparently so. All right, so which program outputs assembly code from an executable file? That's objdump. Objdump will take the executable file and extract the assembly code from it. Which register is the frame pointer? The base pointer. That's the bottom of the current frame. EBP. All right, what code creates a new stack frame? That's the prologue. When you enter the function, that's what adjusts the ESP and EBP to create a new stack frame. The epilogue is at the end. That's what cleans up the stack frame to restore the context to the calling program. All right. Anyway, there's a manual. Okay. And okay. All right. So let's carry on. All right. So there's more instructions, of course. You have more math available. You can add and subtract. Like we said, you can increment and decrement and negate. And you can do integer multiply or an integer division. So those are available, although you don't very often do the multiplication or division. All right. And you can also do bit shift. This is where you shift things to the left, either arithmetic or logical. An arithmetic shift will pad it with, I think, zeros, and a logical will copy the high order bit, something like that. I think we talked about it before. You got shift to the left and you got shift to the right. You have value shifted by a certain number. So the arithmetic one, shift to the left one will double it, and shift to the right one will have an integer. The logical one is a bit more complicated. You can do an AND, which does AND bit by bit, which we've talked about, I think, in the binary games. An OR, an XOR, or a NOT. Those are the bit flipping operations. NOT will flip every 0 to 1 and every 1 to a 0. XOR will combine two bytes or two words. So if the two bits are the same, the answer is 0. And if they're different, 1 is a 0 and 1 is a 1, the answer is a 1. All right, and so on. So here's the load effective address instruction, which is mighty strange. So if ECX points to 808, then you can load the effective address of 8 EAX. And that will take EAX, interpret it as an address, add 8 to it, and then instead of fetching the memory from that location, it will just fetch the address. So it's a strange way of just doing math. EAX plus 8 goes here. And here you take EAX plus EDX goes here, so that'll be 5 plus 4, that'll be 9. Here you load, remember this means start with nothing, add EAX times 4, so it's going to be 20. Here you have 8 plus ECX, and ECX is 808, so that's going to be 810, because 8 plus 8 is 10 in hex. But it's minus 8, so it'll be 800 in EAX. Then you take 4 away from ECX plus EDX times 2. So ECX is 808, EDX is 4 times 2 is 8, so that'll be 808 plus 8 minus 4, that will be 80C. All right, that's another way to figure those things. All right, and then you have loops. So you can compare things with compare or test. This one does R2 minus R1. This one does R1 and R2. The main thing I know is that if there's zeros, you get they're both true. Anyway, then you've got a flag that's set up here, whether it's equal to 0, is negative, an overflow occurred, or an arithmetic carry has occurred. The main one I use is 0. That's the easy one to understand. And so you can jump. This is an absolute jump that will just jump from this location to another, like a goto. And you can jump either to a named location or a location in a register or something, or you can use a star to jump to an address. And then there's conditional jumps, and the main one I use is jump 0 or jump not 0. It's JE or JZ here, jump if it's equal to 0 and jump if it's not 0. Those are the easy ones to understand. Is R1 source and R2 destination? Well, I don't, here, yes. We're using the AT&T syntax, so yes, R1 is source and R2 is destination. Yeah, that's in the Intel syntax, which is what we're using. Good? All right, and so there are other ones, jump if greater than 0, jump if less than 0, and so on. All right, and that's goto essentially. So here, if you have C, you'll say if X greater than Y, then do this, else do that. You could do it with a goto. If x less than or equal to y, then goto here. Otherwise, do this and goto done. This is how you do it with gotos, which are now considered poor syntax for C, poor style for C. Gotos make it hard to understand your code. This if-then-else statement is much more understandable. But this is what you have to do in assembly language. So in assembly language, here we're going to have this thing. If x is greater than y, then set the smallest to y, otherwise set it to x. So here's what the assembly code looks like. We're going to put in EAX, a variable at location 8, and that's going to be x, the other one's going to be y. So we're going to move, say, x into this, then compare y to EAX. Now, if it's less than or equal, I'm going to jump down here. Otherwise, I'm going to put one of the variables into EAX and then jump to the end. And this is how you do it. That's why they gave you that code here. The way you actually do it in assembly code is this way. You do a go to this statement, and here you do it once and then go to jump past it. That's how you have to use two go-tos. That's what you have to actually do in assembly language, because you don't have the if and the curly braces to reference the block. All you have is compare and jump less than equal. And you got an absolute jump. So this compare and jump less than equal combine to an if statement, where if one of these is greater than the other, then it will take the jump, otherwise it won't. And then you do copy the one that is considered smallest here and then skip over that command. Otherwise you go here and execute this command and go to return. It's a little bit clumsy. This is the way we used to write everything back in really primitive languages, and assembler gets you back to there. So there's a conditional move is another way to do it. You would save EBP, update EBP. Now you're going to copy y to EAX, compare x with y, and now you can do this conditional move. If it's less than or equal, do the move, otherwise don't. So this is a way to do it without those two jump statements. This conditional move is a way to make it almost as simple as it was in C. All right. And so it's a bunch of these. Conditional move if it's equal to 0, move if it's not 0, move if it's negative, move if it's not negative, and so on. Many options. Yeah, I never had that. Of course, I started with 8-bit assembly that was simpler, and there was no conditional move, so we just did it with those jump statements. All right, and then there's loops in assembly. So here's one way to make a loop. While I is less than or equal to n, let the total equal something, and I equals I plus 1. That's one way to just make a loop, a while loop. Here's a for loop. For I equals 1, I less than or equal to n, I plus plus, total plus equals I. This is another way to express the same loop. And both of them will create the same assembly code, because in assembly, you don't have the curly braces, you don't have while, you don't have for. All you got is like those jumps and maybe those conditional move statements. So here's what you have. This is the preamble that creates the stack frame. All of this, including the sub 10. So this moves the ESP into EBP, starting a new stack frame at the next available memory address. And this subtracts 10 from ESP, so reserving 10, which is in hex. So it's 16 bytes available on the stack. That's the size of the stack frame. So now I put a 0 in one location, that's total. I put a 1 in the other local variable, which is I. Now I jump down to plus 32, which is down here. So now I put move 4 from EBP, which was I, move I into EAX. And then compare the other number to EAX. And jump if less than or equal up here. So this is what checks to see if I is less than or equal to n. And if we're still in the loop, it will jump back up here. This is the loop, back to 22. Here it will add something to the total and increment I and then go again. So that's the way it works. All right. You can read this assembly code and you see it does the same thing as the C code. It's just a little more primitive. It takes 2 or 3 statements here to add up to each C command. All right, and then there's functions. So you can leave a function. To prepare to leave, return is what actually returns, jumps back, pops EIP, pops the next value on the stack, puts it in EIP, that's the return pointer. this leave repairs, what it does is it restores the stack frame to what it should be. It takes the EBP and puts it in the ESP and pops the stored EBP. So that'll restore you back to the condition that the stack was in before you entered this function. And here's call. That will go there. So this will push the EIP on the stack and then move this address into the EIP. So it'll enter that function. It saves the return pointer on here before it goes, so it knows where it's trying to come back to, and then it jumps into that function. And in the function, it will create the local stack frame, do the processing, and then return. All right, and so let's take a look at adder. I should have that here, so let me get out of this and clear, and cat adder.c. All right, so here I have a main function with a local variable called x, and I'm going to call adder with no parameters. Here's adder. Adder is going to be just return a plus 2 with a local integer, but notice the a is never assigned to anything. It doesn't come in as a parameter, so that's a little strange. And then I'm going to print x that came back. Now here's a sign. A sign up here is going to set int y equals 40 and return y. But notice there's a lot of bugs in this program. This assign returns a value, but here I call it without saving the return value anywhere. So even though it returns a 40, I'm not going to see it. So this is a strange situation. This thing has strange bugs. So let's see if we can figure out what it's going to do. When I run this, it's going to call a sign. That's going to create, I remember what's going to happen here. This is going to create a stack frame with room for an integer variable and put a 40 in it and then return. And then I'm going to call adder. Adder is going to enter and create a stack frame, and the 40 that was assigned up here is just going to be left there. So it's going to end up with a 40 as an input. Even though I didn't pass it in as a parameter, it's left over from this function. So that'll be fun to watch. That's the idea. So let me run through it. We're going to debug this function. Put a break at the start of adder, assign, all right, and a break at the start of adder, all right, and turn off the colors, all right, and then run. All right, and now I'll disassemble assign. All right, so I'm just about to enter assign, you see, and that's going to push EBP, save the old base pointer, begin the new stack pointer, begin a new frame at the currently available, subtract 10. This is going to create a stack with size 10, which is 16, and then it's going to move 28, which is 40 in decimal, into that location on the stack, and then return. So that's fine. So let's print ESP and print EBP. All right, so this is the calling function that goes from 4A8C to 4A8. And now I can examine memory here from EBP minus 30. All right, so here you see contents of the stack, and EBP is here for A8, and this is the stack frame of the calling function. The main function has this information, like a couple of ones are stored up there and a 0. All right, now I'm going to go through this function. I'm going to go forward 1, 2, 3, 4, 5 commands that will perform this activity. Next I5. Now I'll disassemble assign again so we can see where we are. All right, so I proceeded to this point. I've done the calculation. Now if I look at ESP and EBP, you see it's 478 and 488. That's the stack frame of size 10, and it's before this stuff, 4H-C to 4A8. So there's a new stack frame made above that one. And on that stack, if I do the same EBP minus 30, okay, let's view some data here. and you will see the 28 here. That value has been saved on what is currently the stack frame of this subroutine. Does the x/16x mean it's going to show 4 rows times 4 columns worth of values? Yes, it does. It will be 16 32-bit words, each of which is 4 bytes. That's what 16 means, 16 words in hexadecimal, and this is a word. So that's what it is, 4 by 4 rows, exactly. And by the way, I should mention the way you count this, this is 558, this byte is 58, this is 59, this is 5A, and this is 5B. This is 5C, D, E, F. This is 6, 0, 1, 2, 3, and this is 6, 4, 5, 6, 7. That's how it works. Because Intel is little endian, so it reverses the order of the bytes to show you the actual number. If it was a 32-bit integer, it would be laid out correctly with the most significant bit on most significant hex characters on the left. All right, anyway, that's what's going on. And so you see there is a 2C up here on the stack memory. And there's the 28 here. That's the 40 that's been left there. And right now that 40 is on the stack frame. It's between 478 and 488. So this is the current stack frame. And so right now that's a local variable of this routine. But when I proceed a couple more instructions and return, it will no longer be in use. So I continue. And now I've made it into the adder routine. So now I can disassemble adder, adder. All right, and so I'm just at the start of the adder routine. Now if I look at ESP and EBP, those are again the values for the calling function. But if I do this x16x from EBP minus 30, there is a 28 still up here, left over from before. And the point is, it's going to think that is a parameter that was left on the stack for this one to find. It's going to think the calling routine pushed that parameter onto there and then called me. But it's in fact the previous function that had it left over. So now if I do 5 more steps, next I5, I'm right here in this state, in this function. If I go forward 5 and disassemble that function again, I'm now down here. And now if I look at the stack pointer and the base pointer, it's now 478 and 488. And now if I do the same examination here, x16x, EBP minus 30, then I'll see the 28 there. And that's between 478 and 488. So that value is in here. It's calculated that value where the local variable is. All right, so that's what happens. And I think if I continue, it's going to print out 42. Yeah, that's how it gets 42. So this is an important issue. You have leftover data in memory. It does not clear memory when it's done using it. All right, so let's try another Kahoot, which is 8B, which is down here for some reason. Unless something has changed, I think these are the only 2 players. Apparently not. Nothing appears to have changed. We will charge ahead. All right, so one instruction will double the value of EAX as long as it's below 128. actually larger values would work too because it's a 32-bit register. But anyway, it's shift arithmetic left. Shifting by 1 bit doubles the value. Shifting by 2 bits would quadruple the value. All right, which instruction results in 0? They all will, more than one. All of these will result in 0. Comparing them, testing, or subtracting them, if the values are the same, you'll get 0. All right. All right, which one jumps unconditionally? Jump. That's unconditional. These others are jump if 0, jump if equal to 0, jump not equal. Jump is the one that always jumps. All right. All right, so let's go back here. All right. So then there are some fancy features available in assembler, which I don't think I've ever used. You can do recursion. This is going to total the integers 1 through n. Summer is going to call itself. So if n is less than or equal to 0, you return 0. Otherwise, you take the summer of n minus 1 and add n. This is recursion, so it will call itself over and over again. Having many copies of the same function in memory at once. And so there's even an animation to show this going. Let me bring that up. If I go here to the book, all right, it's going to be C8 IA32. I should be able to just go to this location, actually. Let's try that. Yeah, there we go. So there should be an animation down here. There it is. All right, good. Trying to make it fit on the screen. There we go. So here it is going through the steps. Push EBP. Going through the steps. Now it's going to compare something and jump if greater. It's yes, so it's going to jump down to plus 19 down here. Okay, then it's going to move a local variable into EAX and subtract 1 from EAX, which is currently 2. Should have gone down one, I would think. Move EAX to ESP and call summer plus 1. That's going to go back up here and run summer again. And so this is the stack. So it's had a copy of summer here, and now it's created another copy of summer up here in memory. And it's going to make multiple copies of it, of the stack frame. It's going to make new stack frames for each of these in memory, going through the same code in different context. That's how it's good. That's how it actually looks in assembly code when you have a recursive function. So we'll see how deep it goes here. Here's where it calls summer again. So it makes another stack frame up here. It puts the return address on the frame, and when it enters summer, this is going to do the preamble and create the new stack frame here by adjusting ESP and EBP. So we have another stack frame up here, and this is going to store the local variable. This was 2, 3, 2, 1. This one's going to have a local variable of 0. Loading up. And maybe it's not going to load the 0, but the fact that it's 0, I mean, there it is. It loads the 0 locally, so now it's not going to call another one. All right, The stack frame is the little square, not the whole square. The stack frame is the part after the return address, so it's 3 bytes. That's the stack frame, and this is the return addresses right at the end of each stack frame. You're creating whole new stack frames each time. Each time you call a subroutine, it creates a stack frame to store the local variables. Now it's going to return from them. One by one, it's going to return each of these. This is no, it's going to move some stuff. And it's going to leave this junk behind in the stack. It's not going to erase it. So these stack frames are storing copies of the local variables. See, now it shows you which one is, the bold one is the one that is active. So this is leftover stuff. It used that return address to cut the function above it. This is the currently active stuff. Now when it gets to the return, it's going to go to this return address stored here, which will be pretty soon. Leave and return is coming up. Yep. Leave clears up the stack frame, moves the pointer switch, now no longer used. Now it's returned, so this part of the stack is all freed for reuse. And it's going to go through one more set of returns, maybe 2. Yep, now it's going to return from this one back to this active stack frame. Return from that one, and now it's out here showing you that the total is, I guess it's going to do a little more. It's eventually going to print out the answer here, I think. I ran the sum of 3, and that should give me 3 plus 2 plus 1, which should be 6. I should see a 6 appear down there, but it looks like it doesn't go that far. But anyway, that gives you an idea. All right. All right. So then you can have arrays in assembly. If you have something like int array 5, or int star array 5, then you can have type array of n is sort of the way you do it. And so your %edx will contain the address of array. In this case, ECX is the index, EAX is x. So now if I set x equals array in C, x is going to be set to a pointer, which is an int star. So that's going to move EDX to EAX. EDX is the address, so it puts the address in EAX. X equals the first element of the array, array 0. That's going to be an integer, so that will be move the memory pointed to by EDX into EAX. Here you're going to x equals array 1, so that'll be EDX plus ECX times 4. The ECX is 1. That'll jump forward 4 bytes because we have 4 bytes for integer. This will put the array element 1 in EAX. Here we're going to have array element 3, and we're going to have a pointer to array element 3. So we take C and add it to EDX. C is 3 times 4. So that will take us to the third point, and then we get the address of that and put it in EAX. That'll be a pointer to array element 3. Here we're going to have the base pointer plus 3, and in this case we're going to add EDX, which is the base, and we're going to add C to it. When you add 3 in C, it will automatically assume 3 times the size of the elements in that array. So it'll move by groups of 4 bytes. So you add 12 here instead of 3. And here you got the pointer to array plus 3, which is the same as what you had here. It's going to be C, take the address, add C to it, and put it in EAX. So these are various ways to get it in assembly code, and that's why I say C is the language to learn, because C is very close to assembly. All right, so here's an array with 5 integer elements, each 4 bytes long, 0, 1, 2, 3, and 4, and that gives you bytes numbered from 0 through 19. Yeah. All right. And so there were also matrices, which are 2-dimensional arrays, and I said I'm not going to worry about matrices in assembly. That's a little too crazy. And there are structures in assembly. You can have a data structure that has a 64-character string, and then an integer and another integer, and then a floating point. You can have that sort of thing, and it'll just look like this, 64 bytes, and then 4 bytes for an age, 4 bytes for a year, and then however many bytes it is for a floating point number, either 4 or 8, I forget how many you have there. And so you can initialize a student here in C by copying things into the various locations. And here's how that would look in assembler. You create a stack frame and you add 24 bytes to the stack frame, so you have room for 24 bytes of local data. And then you copy the first parameter to EAX and the second parameter EBX, finding them from the base pointer. And then you copy immediate value of 40, which is 64, to ESP, another local variable, ESP plus 8. Then you copy name, this parameter that came in, which is where you're going to put the name, yep, pointer to the name. So you're going to put that in a local variable, ESP plus 4, copy S to the top of the stack, and then call a string copy function. This is how you do a call, which is important to understand. When you're going to call a function, you put the parameters on the stack, and then you call it. And then what happened to us in that previous example a bit back is there was data on the stack that was not put there before calling the function, but the assembly code doesn't know that. When it goes in the subroutine, it will just take whatever data is on the stack, assume that's the data you want to work on, and work with it, and it will not know whether that data was actually put there intentionally by the developer or whether that was just data that happened to be left over there. All right, so now it's going to copy S into EAX, copy the fourth parameter EDX, and so you go, just copying all these parameters to various locations. That's all it's going to do. This is what's going to assign, build that data structure, one element at a time. Just a whole lot of move instructions and then returning. Now there is an issue of alignment. 4-byte data types are 4-byte aligned. So if you have a name that's only 63 bytes long and then you have an integer after it, you're going to have a padding byte because it wants to have a 4-byte integer start at a multiple of 4. So the fact that you only had 63 here means you're just going to have an unused one in the middle to get this back to alignment. All right. And as we talked about buffer overflows, we've been through this lots of times. Let's take another look at this. So there's a function called secret. Let's get out of here and clear. Okay, /secret. All right. Oh, there's no such file. All right, well, let me get it. I don't have it on this machine for some reason, but I stuck it on my server so I can download it anytime. That downloads the zipped version. Here's the unzipped version. All right, that creates secret, which I chmod to make it executable. All right, now I can run it. All right, and it asks me for a number. I'll give it 1, and it says I'm wrong, okay? All right, then I'm going to put in a long thing. So if I run it and give it an A, it doesn't crash. So I can put in longer stuff. Let's say A. Okay, and I need something even longer. G, H. And now I get a segmentation fault. So this long variable overflows the buffer and causes it to crash. All right. So you can see the source code here. End game, you win, void error. The buffer is only 12 bytes long, and here it is reading into the buffer. So it only reserved enough room for 12, so when I exceed 12, it starts intruding on memory that was not reserved for this purpose, and eventually I hit something important like a return pointer that will cause it to crash. So we can put it in a debugger. I'll just save this. So gdb minus q secret. Whoa, all right. All right, and then set style enabled off. Okay, then run and put in my thing there. And now it crashes with 49, 49, 49, 49. And this is 41, 2, 3, 4, 5, 6, 7, 8, 9. So it was the I's that ended up in the instruction pointer. So now I can control it. And if I disassemble end game, okay. All right, this is the function I want to hit to win. So that's the address, and that's this number ending in 54. Okay, I'm going to copy it. Well, we'll just see. Yeah, now, all right, I have to disable ASLR and make Python exploit script. Okay, I'm going to get a text editor around here so I can save some things. The first thing I want to save is the injection, and then instead of the IIs, I'm going to put in this value here is the function I want to run. There. Okay, now I've saved some data. So now let's get out of the debugger and get rid of address space layout randomization. So that's sudo su minus, sudo su minus. Okay, and now this command will turn off the address space layout randomization and exit. All right, and now I can make a Python exploit script. All right, secret exploit.py. I guess I gave you the exploit script, okay. Okay, so there it is. Here's the secret exploit script. So I have the A, B, C, D, E, F, G, H. The next 4 bytes are the instruction pointer, and I can see at the top of my screen here, here's what I want, 0804 85 54, and I have to put them in backwards, so it's 54 85 0408. So this will print the prefix and then that. So I can see what it looks like if I just run this program, Python 3 secret exploit. It prints the H's, and then the rest, other 4 characters, a lot of them are unprintable. So what's better is to put it in a file called exploit, and then use XSD to examine that file. And now I can see it in hex, so I can see it has letters up through H, and then it has this stuff, 0804 85 54, of which only one of those is a printable character. XXD does this. XXD lets you see the value of a file, the data in a file in hex value. So you see it in raw hex and ASCII over here. So you use it if you have unprintable characters in the file that you want to see, which is what happened here. Good. All right. And so now I can just run the secret, and I can take the input from that exploit file. And now I will win, because this will jump to the function that prints out you win. I control the instruction pointer with the overflow. So it's another example of the overflows we've talked about before. All right. So if you want to prevent buffer overflow, there are quite a few defenses. The one I turned off here was address space layout randomization. That will, every time you launch a process, it'll move it to a random location in memory. So every exploit that requires injecting the address of something will be unlikely to work because you don't know where you are. So the address probably won't be the address you're looking for. Stack canaries are a value placed at the end of every stack frame. Really, they only do it for stack frames that have character arrays in them. They pick ones that look dangerous, and they put a canary value in there. So it checks when it tries to return if that canary value has changed. And if it has changed, that means somebody had a buffer overflow and they overwrote more data than they were supposed to, and it will just stop instead of continuing to run. So that prevents this kind of buffer overflow exploit. Then there's data execution prevention, which it gives permissions to memory regions. And what you typically do is write or execute. So the stack is writable, but not executable. So you can store data on it, like type in strings that the user puts in, but if you try to execute that as code, it won't execute. That's the point of data execution prevention. And these were very effective at stopping these buffer overflow exploits. The other thing you can do is use safer C functions. Instead of using getS, you use fgetS with a number here to say how many characters to read. Instead of reading all the characters the user types in, you only read a certain number of them. Instead of using scanf, instead of scanning a string of unlimited length, you scan only 12 characters. You specify the number of characters here. Instead of string copy, you use string ncopy with a number. Instead of strcat, you use string ncat. Instead of sprintf, you use snprintf. All these will limit how many characters you copy, so it's easier to avoid buffer overflow exploits. That's one technique people have used to limit this, and you can make safer source code. So here, if I read it from the user, I use 12s, then it's not going to fall for it. So let's try that. Let's get my long string here and put it in memory. All right, and now if I run secret2, and I put in I, J, 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 K, 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 it doesn't crash, because it's only going to read a certain part of this and no more. All the rest is not going to be loaded into memory, so it won't overflow the buffer no matter how much I put in. That's the idea. All right, so let's try the last Kahoot, which will be here. All right. I think those are the only two I'm likely to get. I'll wait another measure or so. All right. All right. An array is declared here, int array 5. So which C expression is a pointer to the first element in the array? This one, array. That points to the start of the array, which is where the first element is. This is the value of the first element. Let's see, this one here, I'm not quite sure what that would do. Ampersand array, I think would be a pointer to a pointer is what it would be. And this would be star array. Yeah, I'm not quite sure what they would do. One's dereference, one referencing, but this is a pointer. But array is one that points to the start of the array, and that points to the first value in the array. All right. All right. EAX points to the start of the array. So what assembly instruction will put the first element of the array into EDX? I like the first one. Yep, that's it. Just takes the first element in the array, and it's long, so it's the first 4-byte, first 32-bit value found at the start of the array into EDX. That's what it does. All right, good. All right, and which defense puts an extra value at the end of a stack frame? That's a stack canary. Named after a canary in a coal mine, you'd put a canary in a page and put it on a stick, and you shove it ahead of you in a mine to see if the error is bad. So that's the idea. It tells you if there's been a buffer overflow exploit. All right, and so this is going to be the same people winning again, obviously. There's only 2 players. So people go up to 9. All right. So let me stop this recording.